Continuing on, NO, nitrogen has 5, oxygen has 6. So we have 11. Now, we haven't had a situation where we've had an odd number of electrons. So let's go ahead and try to deal with this. So we have 2, 4, 6, 8, 10, sorry, 2, 4, 6, 8, 10, 11. So nitrogen's not full. All right, so let's go ahead and share some oxygens here. Now, you'll notice there is no way with this number of electrons to make full octets. We don't have an even number. You have to have an even number to have everybody have 8. So, we're going to have a single electron somewhere. This is a radical species, so radical means it has an unpaired electron. So it's very reactive. Now, what we can also do is we can also draw this structure where the radical is on the oxygen and nitrogen has the complete octet. So we'll draw resonance for that. Now let's evaluate the charges and see if one of these is better than the other. Don't get me wrong, they're both terrible and they're both highly reactive because you have an unpaired electron and it really doesn't like it. But formal charge wise, 1, 2, 3, 4, 5. So nitrogen is 0. Oxygen, 1, 2, 3, 4, 5, 6. Oxygen is also 0. Isn't that interesting? How about over here? Nitrogen, 1, 2, 3, 4, 5, 6. Nitrogen is -1. Oxygen, 1, 2, 3, 4, 5. Oxygen is +1. Remember with split charges, the negative should be on the most electronegative atom. Nitrogen is not more electronegative than oxygen, so this is not this is an even less stable formation. So we'll put the star by this one because it's the most stable. All right. How about this one? ClO2. Cl has 7. Then you have 2 oxygens. So we've got a total of 19. Okay, that's also going to be a radical species because we don't have an even number of electrons. I'm going to put this just for symmetry purposes with, although for electronegativity, oxygen probably should go in the middle, so let's do that. Okay, so 2, 4, 6, 8, 10, 12, 14, 16, 18. Here, we'll put it on. We'll leave that on an external atom there. Okay. So we could do that. That leaves us with formal charges. 1, 2, 3, 4, 5, 6, 7. Chlorine is good, so it has 7. Oxygen, 1, 2, 3, 4, 5, 6. Good. Oxygen, 1, 2, 3, 4, 5, 6. Also good. So even though you have the unpaired electron, those are all still formal charge of 0. So they're surprisingly stable. All right, what if we go the other way? And what if we make this middle oxygen the one with the radical on it? So there's the unpaired one. Here, when we do this, we have chlorine is still at 0. Oxygen, 1, 2, 3, 4, 5. So this oxygen is +1. And this oxygen here is at -1 because it has 7. All right, so split charges are always worse than no charges. Let's do the last one. So this one's going to be more stable, but we've got another option. Let's make the radical on the chlorine. All right, when we do that, we have this oxygen being -1. This oxygen, 1, 2, 3, 4, 5, 6 is 0. And this chlorine, 1, 2, 3, 4, 5, 6 is now +1. +1. Chlorine is more electronegative than oxygen, so this is the worst one of them all. We're going to put a star by this one. Now, if you said for symmetry purposes you wanted chlorine in the middle, let me show you what happens. So if you 1, 2, 3, 4, 5, 6. And then we put the radical on chlorine in this form. Notice these are not, this is not resonance. This is not resonance because they've changed positions. Your central atom is different. Now, chlorine on the other side, that's not an issue. But we're gonna, since your central atom is different. All right, so this oxygen would be -1. This oxygen would be -1. Chlorine, 1, 2, 3, 4, 5, is now +2. Gosh, that's awful. All right, so let's try to put the radical on an oxygen. Okay, so this oxygen is still -1. This gets the chlorine to +1. And the oxygen with the radical is at 0. You can see that this is still the preferred structure. This is one of the reasons why you have the least electronegative atom in the middle.